Have you ever really thought about the math behind a coin flip? Or a roll of the dice? Or, the big one, your actual chances of winning the lottery? Well, if you have, you are in exactly the right place. Today, we're going to dive headfirst into the amazing world of probability.
So here's our roadmap for today. First, we'll get a handle on what a guess really is, the foundation of randomness. Then, we'll get into the super important tools for counting possibilities. After that, we'll use those tools to solve a real problem, learn the golden rule for calculating odds, and finally, we'll see it all come together with some fun, rapid-fire examples. Let's get to it. All right, first up, what is a guess? Look, before we can even start to calculate odds, we have to be on the same page about what a truly random event actually is. Seriously, this is the foundation for everything else we're going to talk about. Just think about these for a second. Flipping a coin, rolling a die, picking a random card from a deck. We see this stuff all the time, right? But mathematically speaking, what's the one thing they all have in common? Well, in the world of math, they're all called random experiments. And for something to qualify, it just has to meet three simple conditions. 1, you know every possible outcome ahead of time. You know it's going to be heads or tails. 2, you can't possibly know these specific results before it happens. And 3, you can do it again and again under the exact same conditions. That's it. That's the bedrock of probability. Okay, so we've got a handle on what randomness is. But to figure out the probability of something, we first have to count up all the possible outcomes. And for that, we've got two incredibly powerful tools in our toolkit. And here they are, permutation versus combination. Now listen up, because this right here might just be the single most important idea in this entire explainer. It all boils down to one simple question. Does the order matter? If the answer is yes, we're talking about a permutation. If it's no, it's a combination. Let's dig into what that really means. So a permutation is all about arrangement in a specific order. The best way to think about this is electing people to specific jobs. Like a president, a vice president, and a secretary. It absolutely matters who gets which job, right? Person A as president and person B as VP is a totally different outcome than person B as president and person A as VP. The order is everything. And this slide shows it perfectly. Let's say you've got 3 books. We'll call them A, B, and C. How many different ways can you line them up on a bookshelf? Well, as you can see, there are 6 totally distinct ways. Putting them in the order A, B, C is a different arrangement from A, C, B. Each one of these unique lineups is a single permutation. Now let's flip that idea on its head and talk about a combination, where the order means nothing. This time, imagine you're not assigning specific jobs. You're just forming a 3-person committee. In that case, a committee with A, B, and C is the exact same thing as a committee with C, B, and A. The group itself hasn't changed. Let's go right back to our 3 books again. But this time, your job isn't to arrange them. It's just to choose 2 of them to pack for a trip. So how many different selections can you make? Well, you could take A and B, or you could take A and C, or B and C. That's it. There are only 3 combinations. Because picking book A and then book B is the exact same result as picking B then A. Either way, you're walking away with the same 2 books. See the difference? Okay, that was the hard part. Now that we can tell the difference and we know how to count our options, let's put these awesome tools to work. We're going to solve a problem that sounds way, way trickier than it actually is. So here's our puzzle. You've got a group of 6 men and 4 women. The question is, how many different 5-person committees can you possibly form that have at least 1 woman on them? It's that at least one part that makes your brain kind of freeze up, right? Don't worry, there's a really clever trick for this, called the indirect method. Instead of trying to count all the committees with exactly 1 woman, then 2 women, then 3, then 4, which would take forever, it's so much easier to just figure out the total number of committees you could possibly make, and then subtract the one type of committee we don't want, a committee with 0 women. And when you run the numbers, it's actually pretty simple. Since the order of people on a committee doesn't matter, we use our combination formula. It turns out there are 252 total ways to pick any 5 people from the group of 10. And there are only 6 ways to pick a committee that's all men. So you just do 252 minus 6, and you get your answer, 246. That's it, 246 possible committees that have at least 1 woman. Not so scary after all. All right, we have totally mastered the art of counting, which means it is time for the big payoff. We are finally ready to calculate the actual odds of something happening, and we're going to use the golden rule of probability. And here it is, the classical probability formula.
Now, I know it looks a little formal, but the idea behind it is about as simple as it gets. The probability of any event is just the number of ways you can get the outcome you want, divided by the total number of outcomes that are possible. That's it. It's just what you want over what's possible.
So let's stop talking theory and put this beautiful, simple formula into practice. We're going to move from theory to reality with a few quick examples to see just how powerful this thing is. Okay, first one. You roll a standard six-sided die. What's the probability you get an even number? Well, how many outcomes do we want? 3, right? A 2, a 4, or a 6. And how many total outcomes are there? 6. So it's 3 divided by 6, which simplifies to 1/2. A 50% chance. Easy. Next up, you pull one card from a standard 52-card deck. What is the probability that it is a heart? Okay, how many hearts are in the deck? 13. That's our number of favorable outcomes. How many total cards? 52. So 13 divided by 52 simplifies to 1/4. A 25% chance. You're getting the hang of this. All right, one last one. And this one's just a little trickier. If a couple has 2 children, what's the probability that they have at least one girl? To figure this out, let's just write down all the possibilities. There are only 4. You could have boy-boy, boy-girl, girl-boy, or girl-girl. Now, which of those outcomes fit our rule of at least one girl? 3 of them do. So the probability is 3 favorable outcomes out of 4 total outcomes. 3/4, or a 75% chance. So there you have it. The logic is always the same. You just count the outcomes you're looking for, and you divide by the total number of possibilities. We've used this simple idea to figure out the odds of drawing a single card. So we'll just leave you with this final thought. Using these exact same principles, what do you think the absolutely staggering odds are of winning the lottery? Thanks for joining.